All right, so the last two problems involved a lot of math, but they were boring. Would you agree? I mean, they didn't really require you to do a whole lot of thinking. You just basically followed the procedures that you've learned in the past. You know, you did if it was kinematics, you just did the pictorial representation, you used the three equations of kinematics, and then typically you had to find the acceleration, so you just did the force diagram, F equals ma, and you just do it, right? You just do it. So this problem here is not boring. This requires you to actually think. So I like this problem a lot. All right, so there we go. A 5 kilogram block is held against a vertical wall, like that. Then the initial force is removed, and a horizontal force of 12 newtons pushes the block against the wall. If the coefficient of static friction is 0.8 and the coefficient of kinetic friction is 0.6, what happens? I mean, that's basically what, right? Okay. Now, wow. Let's just think about it. I mean, first of all, again, it says the block is held against a wall. So I'm holding this eraser against a wall. Then it says the initial force is removed, and there's 12 newtons that pushes against it. Now look, you don't know what's going on, right? I mean, it says that 12 newtons is going to push, but is 12 newtons enough to keep the thing at rest, or is 12 newtons not enough? So in other words, we don't know if that half a kilogram block is at rest or if it moves. We don't know. So we don't know if it's a kinetic friction force or a static friction force. We don't know. So we got to find out. So let's do it. So this problem is kind of like when I introduced friction. How did I introduce friction? I held the eraser against a board, right? And I said that the frictional force depends on this normal force. If I don't hold this thing if the normal force is not very big, it's going to fall. And that's how we learned about friction. We learned that friction is proportional to the normal force. Okay, so this problem is kind of related. All right, so let's do it. Okay, so might as well just use Randy Knight coordinate system. There's no reason not to. Okay. What are the forces acting on the object? Well, obviously there's the weight, right? There's the weight, and there's a force, the pushing force, right? The 12 newtons. So again, this is one of these things where you have to kind of pretend that your head's in the wall, right? The pushing force, I'm going to say, is this direction, or it doesn't matter. So this is the pushing force, right? That F, the 12 newtons. Now remember, if there's a pushing force, right, there's a normal force, agree? So, all right. And again, it doesn't matter. I could have put the N here and the F here. It doesn't matter. Okay, now up, again, this thing is being held like this, right? So there's a friction force up there. Agree? So I'm just going to say FF, force of friction, because we don't know if it's FS or if it's FK. We don't know, right? Because we don't know what's going on. We don't know if it's stationary or if it's moving. Wow. Okay. So okay. So is it accelerating in this direction? Obviously not, right? So we can immediately say the sum of the x forces equals 0, which is F minus n. Therefore, F equals n. Now again, pretty soon, if not now, you're just going to be able to look at the force diagram, and you're going to realize that the eraser, or the half a kilogram block, is not accelerating this way, which means, like that. And so you're just going to be able to write F equals n, right? I mean, you should be able to just look at it. But I just did this just because I want to be complete. All right? But anyway, pretty soon you're just going to look at it and say F equals n, bingo, right? You don't have to do all that writing. Okay, now let's see. What's going on here? Oops, forgot my little arrow. Okay, now the thing is, we want to calculate, okay, we want to figure out if it's at rest or if it's moving. If it's moving, that means that this weight has to be greater than Fs max, right? So what we got to calculate is Fs max. And of course, weight. Okay, so the weight is mg, which is a half a kilogram, times 9.8, 9.8 meters per second squared. So it's 4.9 newtons. All right, so that's the weight. So the Earth is pulling down 4.9 newtons. Well, we want to see what's Fs max. Fs max. So Fs max is mu Sn. Okay, what's mu s? 0.8. What's n? F. What's F? 12. Okay, 0.8 times 12 is 9.6. All right, so now, look. The weight is 4.9 newtons. The maximum static friction is 9.6. All right? So, does the weight exceed the maximum frictional force? No! So therefore, the thing's going to be at rest, right? But remember, Fs is less than or equal to Fs max. Remember that little goofy demonstration I did the other day when I was blowing on the case, and then I would push it with my pinky and all that stuff, right? Okay, so look, this is Fs max. But this, the weight, is 4.9. It's at rest, right? So what's the frictional force? It can't be 9.6. I mean, Fs max is 9.6, right? But the frictional force can't be 9.6. I mean, think about it. This here is 4.9, right? If this were 9.6, what would this silly thing do? The block would go up. That'd be weird, right? Okay, so Fs max is 9.6. The weight is 4.9. So what's the static frictional force? It's, well, figure it out. It has to be 4.9, right? Because this is not accelerating. If this is 4.9, that has to be 4.9. So the answer is Fs is 4.9 newtons. Now, is that an awesome problem or what? So you better make sure you understand this. So, I mean, you got to think about it, you know. A lot of people would choose this because they would just calculate Fs max and say, ha, I'm done, 9.6. But that's like the robot answer, you know. You got to think the problem through. If the weight is 4.9 and it's at rest, that means that the friction force has to be 4.9 because the sum of the forces cancel, you know. Sum of the forces is 0. So, good question, huh? Good question. All right. All right, you read that, please. I should warn you, I like putting questions on exams which require students to think. Okay, a simple accelerometer. When a car accelerates, okay, so this is a piece of string attached to the roof somehow, and this is a weight. Okay, when a car accelerates, the string makes an angle beta with the vertical as shown. Given m and beta, find the acceleration. Okay, kind of makes sense, right? If the car's at rest, you know, the mass is just going to hang down. But if it accelerates, you know, whoop, right? Okay. All right, so what's the object? Is it the car or is it the mass? It's the mass, because that's what, you know. Now, don't forget, you have to analyze these things from an inertial reference frame. Is the car an inertial reference frame? No, right, because it's accelerating. So what's an inertial reference frame? Well, you know, if somebody's standing on the street, you know, just standing there watching this thing. Okay, so let's draw the force diagram. All right. And you know you're going to do a force diagram. Well, I hope you do, because, I mean, find the acceleration, right? I mean, they don't give you any like time or velocity or anything like that, so it's not kinematics. But again, we used a force diagram to find acceleration. So I hope you should automatically say force diagram. All right, so here's the object. What are the forces acting on it? You know, the weight and the tension. All right, and the tension. Okay, now, this is angle beta. Right? All right, and the car is accelerating to the right. All right? So, I mean, any other thing? I mean, those are the only forces, right? Just the tension and the weight. Now, obviously, we're going to have to resolve the tension into components, right? So that's not a big deal. We can do that. So this is T sine beta, and this is T cosine beta. Okay, so here we go. So the sum of the x forces, well, what's the only x force? Just T sine beta. T sine beta, and that has to equal ma, all right? Ma, because that's the direction it's accelerating. And what's a? It's the acceleration of the car, right? Okay, all right. And then, okay, now are we done? You know, no, because this has a t in it, and they didn't give us t, right? So that means we have to do another equation. We have to. So sum of the y's. What's sum of the y force? Now wait a second. Is it accelerating this way? No, it's not. So the sum of the y's is 0. Okay, so what's the sum of the y's? We have t cosine beta up, and we have mg down. Okay. So therefore, we know that t cosine beta equals mg. All right, now we're trying to get a. So I'll show you. Okay, you can solve it however you want to. I mean, look, you have 2 equations, 2 unknowns, right? So you do it however you feel comfortable, and that's totally fine. But I'll show you my way. So ma. Okay, so ma equals t sine beta, right? Okay, so I'm going to divide this by mg, and I'm going to divide this by mg. But I'm not really going to, because what's mg equal to? Mg equals t cos beta, right? Now, why is that cool? Well, you'll see. All right, the m's cancel. The t's cancel. What's sine over cosine? Tangent. So I have a over g equals tan beta. So therefore, I have a equals g tan beta. Ta-da! So I don't know. I think that's faster than doing it, you know, substitution or something like that. But you solve it however you want to. Doesn't matter. Okay, so we did it. A is g tan beta. Now the question: can beta ever reach 90 degrees? Why or why not? Well, what's the tangent of 90? It's infinity. So A would be infinite. So the answer is no, all right? So this thing will never go all the way up here, right? It will never go all the way, all right? It can't, because we don't like infinite accelerations, okay? And, you know, if you didn't know that, just plug it in your calculator, right? All right, let's see. Yeah, we'll just do one more. I'm going to get out early today. Okay, last one. Are you excited? I made this one up. All right, so this is a crazy one, all right? But that's okay. It's snowing on Oahu. To celebrate, you decide to slide down the 5.5-mile-long Dole Hill on your toboggan. You know Dole Hill, you go from Haleiwa up to the Dole Plantation. Okay. As you begin, you feel a strong headwind. You also notice small clumps of dirt from the pineapple fields sticking out of the snow because the snow isn't very deep. Find an expression for your constant acceleration. Assume the hill slope is constant. Now, is the hill slope constant? No. Well, we're just going to, just assume it is anyway. Okay, it's close. All right? So there we go. We're sledding down the Dole Hill. Okay. Wow. So we want acceleration. So what's that? Force diagram. But we're on an incline, which is going to make it a, mess, right? Because the normal is not going to just be mg, it's going to be some angle, Okay, no problem. Okay. So, what are the forces acting on you? Well, there's always the weight, right? There's mg. And there's always a normal. All right? Now, look what I said here, though. You feel a strong headwind. That's drag, right? So there's drag going this way. And what else? It says you also notice small clumps of dirt sticking out of the snow. What does that mean? That means that there's going to be friction as well as drag. Right? So, however you want to draw it, I'll draw it like this. So there's supposed to be parallel. So there's the drag force, and there's the Fk. All right? So we've never done, I don't think we've ever done one like that before, right? So there's two forces, air resistance that way and kinetic friction that way. Okay, and let's see. We're going to tilt the coordinate system, no kidding. So let's just do this, all right? So we're going to have a positive acceleration. Doesn't matter, but it just makes it easier, I like positive accelerations. It works nicely. So, okay, so the only force we have to resolve is the mg. No kidding. We're kind of used to that by now. All right, so there you go. So here's theta. So this is mg. So that's mg sine theta. And this is mg cos theta. Whoa! All right? Okay, so again, we have friction, so that means we need a normal, so that means we do the y equation first. Okay, now, is there any acceleration in the y direction? No! So the sum of the y's is 0, so the sum of the y forces is 0. So we have the normal up, and what else do we have? mg cos down. Anything else down? Nope. So it's equal to 0, so n equals mg cos theta. Now we've seen that before, that's not a big surprise. Okay, now we've got to do the long one. So now we do the fx. Now we do it over here. Okay, it's accelerating, right? Or we're accelerating, so we put ma. Okay, so what's the sum of the forces? Okay, so we have what's going down. The only thing that's going down is mg sine theta. So we have mg sine theta, right? And then what's going up? Fk, right? So we have minus mu kn. What else is going up? The drag. So the drag, I don't expect you to memorize the equation for the drag, by the way. So the drag is c rho a v squared over 2. Okay? All right. So let's work it. So we're trying to find A. All right. Okay. So let's just plug in all our n. So we have mg sine theta minus mu k n minus mu k mg cos theta minus this thing, c rho av squared over 2. And that's ma, right? That's ma. So now we want a, so we just divide by the m's. So that goes away, that goes away, that goes away. There's no m here, so we put it on the bottom. And there you go. All right, so there you go. All right. Yay. Okay. So let's review. So we, right, draw and make effective use of free body diagrams. So we learned how to draw the free body diagram in Chapter 5. Now we use them. Recognize and solve simple equilibrium problems. We distinguish between mass, weight, and gravity. We learned and we used the models of friction and drag. And then the last one, we applied the full strategy for force and motion problems to problems in single particle dynamics. Okay. And remember, think about it now. You know, this is only motion along a line. We still have to do motion along a plane, you know, 2 dimensions. So, you know, things are getting, the problem's getting long. That's, I guess, all I'm trying to say. Okay, so here, pretty short review, but this is really it. F equals ma. You have to understand that, right? What does it mean? It means that the sum of the external forces equals ma. Okay, all right. The friction models, Fs less than or equal to mu Sn, where mu Sn is Fs max, obviously. Kinetic friction, Fk equals mu Kn, rolling, Fr mu Rn. Okay, equilibrium. It just means it's not accelerating. It could be moving. It just means it's not accelerating. So if it's equilibrium, the sum of the forces are equal to 0. So you saw on some of these problems, you know, we'll have equilibrium in one dimension, but not equilibrium in the other. So not equilibrium, F equals ma, right? And so, you know, in order to use these equations, you have to resolve the vectors that are not along the axis. And here's our equation for drag. And we learned that free fall, you know, like this, also includes orbital motion, because the only important force is gravity. That's it. Thank you.